Well, okay, everybody, it's time to move beyond some of the topics that we've been talking about and think about what happens when our network gets a little bit bigger. So let's talk about VLANs and trunks. Now, when your network does get bigger, when it grows, we have a whole collection of problems that result. First of all, if we're talking about a layer 2 network, the problem is that that's very flat. And what that means is that the devices all do the same sort of job. So switches do what other switches do, and there's no separation of jobs or responsibilities. And that means that it's an Ethernet broadcast domain. So if we think about a broadcast address, when you put that in an Ethernet frame, that becomes a broadcast frame. And in a switched layer 2 network, the broadcast frame goes throughout the entire topology. And that's very, very noisy. A lot of traffic. Multicast does the same exact thing until you start breaking up the network a little bit. Even unknown MAC addresses get flooded everywhere, so that becomes a real problem. On a layer 2 network, it's also difficult to separate out nodes based on security or quality of service or anything like that. We also know that spanning tree will kill off all of our redundant links, and so that means that we don't have any load balancing, we don't have any redundancy. The solution is VLANs, and we know about VLANs now because we talked about 802.1q, so that's where we find it. And a VLAN is a logical grouping of nodes. So take any ports that you can think of, collect them together into a logical box, and it doesn't matter where they are or what other switches they're connected to. We can make them into a VLAN, which effectively makes them one network together. So there's a tie between what goes on at layer 2 and layer 3. Now, we've talked about this before. There's a tie between the addressing at layer 2 and the addressing at layer 3, and this is another one of those ties. So there's a tie between VLANs and layer 3 networks. When we define VLANs, usually it's static membership, but we do have the ability to change the membership of ports. Those are called dynamic. VLANs can be very geographic. They can be very local to where you are, a closet or a building. They can also be end-to-end, so they can spread out as far as you want them to. Now, a VLAN equals a broadcast domain. So that means the minute you have a VLAN boundary, that broadcast problem that we were talking about is less of a problem because the broadcast traffic only extends as far as the VLAN on which it originates extends. So that means we automatically shrink the impact of a broadcast frame. So we can sort of say that VLANs equal layer 3 networks because everybody in the same VLAN has the same set of IP addresses or IP addresses on the same network. And to get outside of your VLAN, you need a router or a layer 3 routing device. Okay, so in the graphic here we can see that it doesn't matter how the ports are organized, whether they're next to each other or whether they're spread out. You can think of those as being the same switch or different switches. It doesn't really matter. The point is that however you want to organize your ports together in your head, you can make that logical grouping and put them in a VLAN together. And the definition of your VLAN boundaries can be whatever you want it to be. And a single VLAN behaves exactly like a layer 3 network. That's why I was saying we can kind of say that VLANs equal layer 3 networks. Now, VLANs live on switches. Routers don't know about them unless you have sub-interfaces on a router or something like that. But typically, hosts and routers don't know about VLANs. It's a layer 2 device sort of thing. However, everybody inside a VLAN is all on the same layer 3 network. Now, before we go charging off into VLAN land, let me ask you a question. In the top topology here, why does this work? When we have 2.3.4.5 pinging 2.3.4.6 across a collection of switches, why does that work by default? And the answer is that all the ports in those two switches are all in the same VLAN. So what we're adding to our processing now, at least as far as the switch is concerned, is the idea of a VLAN boundary. So all ports on switches by default are going to be in VLAN 1. Now, VLAN 1 has lots of special names. We call it a management VLAN. The reason it's the management VLAN is because it's native. And what native means is that there's no VLAN tagging on that particular VLAN. So the extra decision that we see here is in the source address table. And all the way at the bottom here, you see an example of a source address table. I've taken a snippet from one of my local switches here, and we can see that there are a couple of addresses that are part of every VLAN. A lot of those are multicast and, of course, the broadcast. But we see some MAC addresses are limited to a particular VLAN, and they're, of course, learned or dynamic. Now, the important point to make here is that if two nodes on the 15 VLAN are talking to each other, that traffic does not go outside the 15 VLAN. Doesn't matter what kind of traffic it is, unicast, broadcast, or multicast, it doesn't go outside the VLAN. So we have this automatic chopping up of the network topology into VLAN spaces, and we control traffic in that way. Now let's remind ourselves what a regular sort of topology looks like. If we have a couple of switches, and we have a couple of nodes on each one of those switches, and the nodes on each switch are in their own network, and then we would connect up a router, and the router would take up a port on each switch and have an IP address on the router for each interface. And the router would be the default gateway, or the router interfaces would be the default gateways for the various hosts in this particular topology. So very straightforward. But now we also know that the switches have, by default, all the ports in VLAN 1. So this is how we've come to know and love topologies. This is the way that we always set them up without really thinking about it. This is a very simple, straightforward sort of idea. But we have a couple of other ways to do this now. So now if we say, well, let's put a router on this particular topology, and I want to use VLANs. So now just think about gluing those two switches together and saying, well, instead of having two switches to do the job, I'm going to have one switch, and I'm going to divide that switch up into a couple of VLANs. So within the VLAN, we have the exact same thing. You can see that that upper topology looks very similar to the one on the previous slide. And all that we did was put things in a VLAN. Now, maybe I shouldn't have used VLAN 1 because it's the native VLAN here, but it doesn't matter because it still has a boundary. And so that's the way that you might have an operating topology with just a couple of VLANs in the same router, and you get rid of the device. Now on the lower topology, the difference here is that I've got a couple of switches, and the magic in between these switches is that we're going to have to do a trunk, and we'll talk about that later on. But you can see that I've got nodes on the 1 and the 2 net on the left, and the 1 and the 2 net on the right, and somehow those are going to communicate. And so the idea is that the two VLANs live on both switches, and we're trunking across the switches in order to allow the nodes to not only talk to their default gateway, but also talk to other nodes that are on different networks. Now, multi-layer switches, among other things, have the ability to do routing between VLANs. So in this particular topology, what I did is I got rid of the router, and I turned on IP routing on one of the switches. And so all of a sudden, what we do here is that your VLANs now are given IP addresses, and the VLAN IP address is the same as the default gateway of those routers. So for example, on the left switch, I would have VLAN maybe 1 and 2 or 11 and 12 or 101 and 102, and the IP address in VLAN 1, say, would be 192.168.1.254. And the IP address in VLAN 2 would be 192.168.2.254. My hosts have no idea that things changed. And all that I've done is gotten rid of the router. And I've given the VLANs IP addresses and turned on IP routing. So now the switch knows that it's going to route between the VLANs. So when a packet comes in on one of the particular VLANs, if the behavior is exactly the same way as it normally would be, right? We don't know this particular MAC address on this particular VLAN, so we'll flood it. The MAC address is known, and we'll send it to the correct port. The destination MAC address is actually a router, and then we'll send it up to the router, and the router will process it. Or in this case, since the switch is operating as a router, the switch will forward it as if it was a router in the same exact way. So in this case, the switch on the left would actually have a routing table. Now, trunks. So a trunk is a point-to-point link. Now, historically, trunks have got a lot of different names. So if you have telephony, you know a trunk is a collection of lines put together, but that's not what we're doing here. The primary use of a trunk in a data network is to convey VLAN information. So it's a point-to-point link between a couple of switches typically, sometimes between switches and a router. And the whole point is that we're going to aggregate data. So that means that you're collecting data at that point for transmission across the trunk. The nice thing about trunk lines is that not only do they convey VLAN information, but we can control the topology, control the VLANs, and control the flow of traffic. And so sometimes we can get an advantage in redundancy if we're clever about how we do this. You can even do port aggregation, which is not something we're talking about right now, which allows us to have multiple lines between switches. Now, trunks need a trunking protocol to convey the VLAN information. And so the industry standard trunking protocol is IEEE 802.1q. So that whole discussion about VLANs includes the tagging and, I think I mentioned it earlier, the priority in there. Now, another trunking standard out there is Cisco ISL, and I'll show you a slide about that, but not very many folks use that. Most of the time, you're going to see 802.1q. Now, in trunking, or in switching in general, there are two kinds of links that we see today. There's actually a third, a hybrid, but nobody uses that one, or nobody should be using that one. An access link. An access link is straight up a member in one VLAN. Think hosts when you think about access link. So there's no VLAN tagging. The important distinction between an access link and a trunk link is that trunks do VLAN tagging and have the priority and everything else in there. So they're not connected to hosts. You connect the switches together, now you're dealing with trunk links, and now you're going to convey the VLAN information. Now, all the devices that connect to a trunk link must be VLAN aware. And the simple thing here is that on a trunk link, you've got a new protocol running. You've got 802.1q typically running there. And if you connect a non-VLAN aware device to a trunk port or a trunk link, it's not going to understand the tagging. So that's pretty straightforward. And so the VLAN aware device will understand the structure of 802.1q, and we'll see exactly what that looks like here in just a minute. Now, all traffic going across a trunk line is now VLAN tagged, unless the VLAN is the native one. So VLAN tagging tells the receiving switch what to do with the traffic. So the sending switch builds the 802.1q header, sticks the VLAN tag in there, sends it off to the destination switch, and the destination switch says, what am I supposed to do with this? Oh, here's the tag, here's the VLAN. Great. Now let me look at that VLAN to see if I understand where that MAC address is on the VLAN. When you're building trunk lines, you don't put them into VLANs. That's a good way to block traffic. So trunks do not belong in particular VLANs. And here is an 802.1q trunked frame. The important thing to pay attention to is the start where the blue line is and the line right above that. Now we know that an IP datagram, IP version 4, has an Ethernet Type 2 control field value of 0800. You can actually see that below all this in the type field. When you are trunking, we're doing what's called internal tagging. So we're going to take this 802.1q header and we're going to stick it inside the frame after the source and destination MAC address. And so we're going to take this and do some internal tagging. But we're changing the frame. We stuck something in there. And so all of a sudden the frame type changes to 8100. And so following down from 8100, we now know that we've got to include this priority, the canonical identifier. This is just an indication of the order of the bits, the least significant and most significant bits, and then the VLAN ID. And then whatever we had before. So the type is 0800, and then we're right back into IP version 4. But that's the important part to realize here. We've got a change to the frame structure, so we're going to have to change the type to 8100, and then we put the tag in there and the priority. Okay, so we might have to take a deep breath on this, because we're going to do an example of how this particular ping from PC1 to PC4 might actually work. Now notice that PC1 is on VLAN 2 switch 1, and PC4 is on VLAN 3 on switch 2. They're on opposite networks and different VLANs. So let's assume that, now we won't do the whole thing, but let's assume that the ARP tables are clear. Okay, so PC1 tries to ping PC4. So 1.1 tries to ping 2.1. It looks in its host routing table, discovers that that is on a different network. And so it realizes that it needs to ARP for its default gateway, right? So it looks in its ARP table, and if the ARP table is clear, it ARPs for the default gateway. So it sends out an ARP for 1.254. The switch 1 says, okay, which VLAN did that broadcast frame come in on? You're on VLAN 2. I'm going to send that out all ports on VLAN 2 except the one that it came in on, and any trunk port. So it goes across the trunk line, tagged with VLAN 2. Gets over to switch 2. Switch 2 says, what's the tag? Oh, that's VLAN 2. Let me send that out all ports on VLAN 2 except the one that it came in on and any other trunk port I might have. In this case, there aren't any. So it dumps it off to VLAN 2, and this broadcast frame finally makes it up to the router. The router responds in the exact same way. This is a unicast now coming back, and switch 2 says, oh, I know where that MAC address happens to live. It lives on the trunk line. So it sends it over to the trunk line, tagged with VLAN 2. Goes back across to switch 1. Switch 1 says, what VLAN? VLAN 2, let me check the source address table for VLAN 2, and then dumps it off to PC1 on port 4. PC1 now sends the ICMP echo request. So the ICMP echo request comes out. It is unicast frame back to the router, but the IP header obviously is 1.1 to 2.1. So it goes out the trunk line, tagged for VLAN 2, goes across to switch 2, dumps it off to VLAN 2, goes up to the router checks its routing table, knows where the 2 network is, and then sends out an ARP on the other side for PC4. Now we'll stop right there. Hopefully you get the idea. So we would do the exact same thing, right? So all the messaging is the same, the ARP requests, the ICMP echoes, and all of that, but now we have to add all the tagging in there. And the fact that on switch 1, when all this was happening, VLAN 3 never saw that stuff over there because it's a VLAN boundary. But the trunk line did see it, and so that's how the processing works. But to get to VLAN 3, we needed a router. So hopefully you followed all that. And this is Cisco ISL, and the only reason I show you this is because all the switches are capable of doing it. This is what we call external tagging, and you can see that the tag is stuck in the front of the frame. It's also much larger than an 802.1q tag. Well, that's our look at VLANs and Trunks. Thanks very much for watching. Subscribe and like if I helped, and may your packets always reach their destinations.